Hello, everyone. Welcome to this webinar with the title of Introduction to Cloud Computing for Earth Observation Analysis. This webinar is presented to you by EO Africa R&D Facility. In today's webinar, we are your host. My name is Mahdi Farnaki. I'm an assistant professor at the Department of Geoinformation Processing, Faculty ITC of the University of Twente. And I have the honor of having two of my colleagues here, Dr. Serkan Girgin, assistant professor and head of the Center of Expertise in Big Geodata Science, and also Dr. Mahdi Khodadadzadeh, assistant professor at the Department of Geoinformation Processing, Faculty ITC of the University of Twente. Okay, what is the goal of this webinar? In this webinar, we want to introduce you to cloud computing and its usage to analyze and process Earth observation data. To achieve this goal, we will have this program. We start with the description of EO Africa R&D Facility, the project which present this webinar. Then I will introduce you to cloud computing. After that, my colleague Mahdi Khodadadzadeh will take over and talk about interactive computing using JupyterLab and Jupyter Notebooks on the cloud. The next step will be provide some examples of Earth observation analysis on the cloud, and Serkan will provide you with some examples and some cloud computing platforms, and he will show the examples live for you. After that, we will have a Q&A session. I just want to ask you to just send your questions right away when you have them on the chat, and then we will come back to them in the Q&A session. Finally, we conclude this webinar by providing some information about the next EO Africa R&D Facility webinar. A short description of the project. What is EO Africa R&D Facility? EO Africa stands for African Framework for Research, Innovation, Communities and Application, and it's an activity by ESA, European Space Agency, to foster an African-European R&D partnership. Under this big project, this big umbrella of EO Africa, we have EO Africa R&D Facility, which is a flagship initiative of EO Africa, and it has a long-term goal of supporting an African-European collaboration. The goal is to enable an active research community and create innovative processes for continuous development of Earth observation capabilities in the continent. This project is a follow-up project to a previous successful project named Tiger Initiative that provided capacity building through research in Africa in the past 15 years. It's being implemented by 6 partners led by ITC faculty of University of Twente. We also have CS Group France, CS Group Romania. We have CERCO, TU Vienna, and Vito as our partner in this project. In the first 3 years of this project, we have these objectives. These are the main objectives of this project. We want to provide a cloud-based EO data analysis environment, a platform to support researchers in accessing and utilizing Earth observation data. Okay, we call it Innovation Lab. We will talk about this Innovation Lab later in our presentations. We want to, we are offering technical and financial support for 30 research projects to address African Earth observation research challenges, mainly related to water scarcity and food security. We are also doing some capacity development activities, mainly providing first phase courses, online courses, webinars, and MOOC. This webinar is the first webinar in as one of the activities in our capacity development trajectory. Okay, you can receive some more information about this EO Africa project, EO Africa R&D project. Please go to our website at eoafrica-rnd.org and read through to get more information. Okay, with this description, let me jump directly to cloud computing. I want to introduce you to cloud computing. We know that we are in the middle of a paradigm shift. We are receiving huge amount of data from different sources. We have satellite imagery, GPS sensors, mobile devices, Internet of Things, and also social network. All of them are providing us with petabytes of information collected daily. And usually this information has strong or weak connection to location. So we can call most of them location-based data or geospatial data. So we are already in big data era, yes? So, but what is this big data? Big data refers to large and complex data sets that are difficult to handle and analyze using traditional systems and methods. When we talk about big data, usually we talk about three main aspects or three characteristics of big data. We call them 3V, which is volume, variety, and velocity. Recently, people also are talking about veracity and value, and then they call them 5Vs together. But for simplicity, I stick to volume, variety, and velocity. What is volume? When we talk about volume, we mentioned this, that big data is a data set that is bigger, that its size is in terabyte or petabyte scale. When we talk about variety, we are talking about having data that maybe is unstructured, semi-structured, or has some heterogeneity. For example, you have different format, different schemas. So these characteristics are pointing to the variety. And also for velocity, it refers to the rate at which you are collecting the data, and also you want to analyze the data. So sometimes you receive the whole data set and then you want to apply the analysis and see the results. So you go for batch processing, and then sometimes you're collecting the data continuously. You have data streams and then you want to process them right away and then do a sort of, for example, predictive analysis. Then you're talking about near real-time or real-time processing. Now, I want to point you to an example in geospatial community. We want to see if that example has these characteristics and if we can call it, let's say, big geospatial data set or not. And this example that I want to talk about is actually the Sentinel mission. Most of you know about, I would say, EO European Copernicus program, which aims at achieving a global, continuous, high-quality Earth observation capacity. Under this program, several satellite missions have launched, and then these missions are collecting huge amount of data. If you look at this graph that I'm presenting here, you can see that only in 2020, the amount of data, Sentinel data, that has been downloaded by users exceeded 80 petabytes. Okay, so it's huge amount of data. Okay, so that's the first characteristic. The second characteristic, variety. Sentinel data has variety. You see, we have different satellites. Each of them has different sensors on board, and then they are collecting data. What is this? The data that they are collecting? It's imagery data, okay, and then it's or SAR data, and then it's unstructured. And also, we are collecting data with different spatial and spectral resolution. Okay, so it's the variety of this data set. And also about velocity, these satellites are collecting information with different temporal resolution. And then we want to apply different sorts of analysis, sometimes batch processing, sometimes online processing. For example, for Sentinel-4 and Sentinel-5, we are collecting air quality data, and maybe we want to do some sort of predictive analysis. So we receive the data, we want to predict the near future. So we have to do near real-time or online processing in this case. So as we see, this example of geospatial data has the characteristics of big data. So we can call it big geospatial data. We can say that big geospatial data is available these days. So what we want to do is we want to use it to tackle real-world problems. By real-world problems, I want to, for example, point to sustainable development goals. We want to, for example, use this data to be able to mitigate the effects of climate change or water scarcity or so on and so forth. So we need to apply this data and use this data in large study areas. But huge amount of data, large study area, it's not possible to use the conventional computational solutions that we used to use to solve our computational problem, to do the analysis in this respect. What should we do? First, what we used to do was like this. We have a workstation usually. We have a workstation. We store the whole data set on that workstation. Then we develop a code or we use a software to load the program in the memory of the machine. Then we run the program and then we generate results. Yes, that's the process. But what is the problem? The problem is that it usually does not have sufficient capacity to address the requirements of big data. And also it's not scalable. You may say that, okay, if it's the problem, I may go for distributed computing. I may establish a cluster of machines, and then these cluster of machines is being handled by or managed by a technology like Hadoop or Scarp or similar technologies. And then I have distributed storage, distributed computing. I develop a code. The code is sent to the nodes of this cluster and then do some analysis. Then the results are gathered and aggregated, and then I have the outcome. Yes, that's a feasible solution and very nice solution. Still, there are some problems. It's hard to implement. For you, it's hard to implement a cluster of machines. It's hard to maintain. It requires extensive knowledge and expertise. It's also very expensive and it's not elastic. Okay, so what would be the solution? In several situations, the solution would be cloud computing. Let me define cloud computing here. Cloud computing is a model for enabling convenient on-demand network access to shared pools of configurable computing resources. The idea is that you have this pool of shared computational resource, and then you connect to it, and then the service is provided to you, and then you use the service. So we can say that we have two main roles here: service provider and the user. The service provider set up the infrastructure, which is very complicated, but they hide it behind a layer of software. So what user do is that user just connect to that software and receive a service. But here, there are different service models in cloud computing. We have software as a service model. In this model, the provider supplies the infrastructure and platforms that run a software, and then the user just connect to that software and use the software. And a good example could be ArcGIS Online. In ArcGIS Online, it's like this, that you just connect to ArcGIS Online and use the functionality. You upload your data over there and run the analysis. You don't know where that ArcGIS Online system is sitting. What is the backbone infrastructure? You have no information about that. So that's one model. We call it on-demand software. Another model, we call it PaaS or platform as a service. In this situation, provider supplies the infrastructure, services, and tools that allow the user to deploy the application. Okay, so you get access to this environment, you deploy, the user deploys his or her application over there and then start using the application. So that's the solution. But we have also a lower level model. We call it infrastructure as a service. In this case, the provider just provides you with the infrastructure, but it's virtual infrastructure, virtual machines. So you get access to the virtual machines, and then you deploy your software, including the OS on that virtual machine, and then you work with the virtual machine. So these are the different models of implementing and work using cloud computing. But what is the advantage of cloud computing? That's very important. Why we should use cloud computing? Cloud computing has some characteristics. The first one is elasticity. With cloud computing, what you can do is that you can start with a minimalistic setting. For example, you go and buy a virtual machine with 2 CPUs and 16 gigabytes of RAM. You start your analysis, then you see that, okay, I need more processing power. Then you may add 2 more CPUs, 1 GPU, and then more, let's say, storage. And then you do your analysis, and then at the end you release those resources, extra resources that you got. So it's elastic, so you can play with the resources. It's horizontally scalable, meaning that the provider can easily add nodes to the system without needing to redesign the whole architecture. It's multi-tenancy. Usually several users are using the system. They are seeing their own environment, but that environment is using a single node in the whole system. It's metered. It means that you pay only for the resources that you use. If you just get 2 CPUs, you pay for that 2 CPUs, or the amount of time that you spend for analysis using those CPUs. It's pay per go. It means that you have no upfront investment. You don't need to buy a server and set it up. So no upfront investment. It's more energy efficient, and it's some sort of outsourcing the maintenance of infrastructure to the cloud provider. So these are the characteristics that urge us to go for cloud computing. Now, let me talk about cloud main, let's say, players in this ground, main cloud providers. The main cloud providers are Amazon Web Services, Microsoft Azure, and Google Cloud. But in parallel to these main players, we also have some other cloud platforms that are specific to geospatial community. We have Google Earth Engine, we have Sentinel Hub, we have Open Data Cube, we have Periscope, OpenEO, Geospatial Computing Platform of Faculty ITC also is another platform developed by Sercon. We will talk about it. Now, let me just talk a little bit about some examples here, okay? Google Earth Engine is a service that is provided to us for free, so we can connect, make an account over there and use it. And it combines a multi-petabyte of Earth observation imagery and geospatial data sets, and it allows us to run an analysis in a planetary scale, okay? So huge amount of data can be analyzed. The other system that I want to show you, the name is Periscope. It's also another cloud computing platform. You can create an account for free over there and use it, and it enables you to, it provides you with virtual machines. So you get a virtual machine with 4 CPUs, 8 gigabytes of RAM, and around 80 gigabytes of storage. And then on that virtual machine, you have access to ready-to-use data sets like Sentinel-1, Sentinel-2 data sets, or Spot or other data sets. And then also it's customizable. You can customize it a bit. And also you have access to some pre-installed applications like QGIS and Snap. Another system that I want to talk about is a geospatial computing platform of Faculty ITC. My colleague Serkan and his colleagues together, they has developed this geospatial computing platform for us at ITC and the whole University of Twente. And then on that platform, we have access to GPU-enabled big data ready virtual machines that are with access to, let's say, some data sets, and then pre-installed interactive and desktop environments. And then we can just easily get access to this environment and run our analysis on that platform. So these are those environment that I wanted to talk about. There is another environment that, let's say, cloud computing environment that I want to highlight, and that cloud computing environment is called Innovation Lab. In fact, in EO AFRICA R&D Facility, we are providing a cloud computing solution. The name is Innovation Lab, and it's designed based on a Metis RE PaaS or Platform as a Service, which is developed by CS Group, one of our partners. It's based on Jupyter Hub with some security and scalability improvement, and it allows the users to develop their code and use the data sets that are accessible via Copernicus DIAS infrastructure. Copernicus DIAS infrastructure is a centralized solution provided by Copernicus to access to Copernicus data and information. And this Innovation Lab is installed on top of one of those GIS platforms. So the user has access to the Earth observation data. So co-located data and computing provide them with the ability to do analysis faster and more efficient. Okay. The main, let's say, functionalities that this system provides to the user are interactive prototyping through JupyterLab, integrated development environment through Visual Studio Code, and remote desktop interface, desktop interfaces. All of the people who actually are part of the research teams working in EO Africa R&D will have access to this virtual research environment, and also some of the participants of our capacity development activities will get access to this environment. Okay, so far I tried to describe a bit about cloud computing, what it is, and then familiarize you with some of the examples of cloud computing solutions in geospatial data community. Now I want to hand it over to my colleague, Dr. Mahdi Khodadatzadeh. He will talk a little bit about interactive computing, which is one of the most important, let's say, solutions usually provided on top of cloud computing platforms. And then he will describe it and show you how it works.
Let me share my screen. Okay, hello everyone. As Mahdi said, I'm Mahdi Khodadatzadeh, and I'm going to talk about interactive computing and mainly Jupyter and JupyterLab. And why this topic? Because in most of the cloud computing platforms, JupyterLab is the tool that is being used to provide web-based interactive development environment for data analysis and code development. What is Jupyter? Jupyter is the project or community that aims at developing open source software and open services and for interactive computing across different programming languages. This project was born in 2014, and well, the name of this project, Jupyter, is the combination of 3 languages, Julia, Python, and R. But however, now recently, we can say that it covers more than 70 different languages. Project Jupyter so far has developed several products. The 3 main products are Jupyter Notebook, Jupyter Hub, and JupyterLab. Jupyter Notebook, probably some of you are familiar with that. Is the traditional tool from Jupyter, a browser-based application that allows you to create and share documents. The documents are called Jupyter Notebooks. That you can, in these documents, you can have code, text, results, and visualization at the same time. The format of this document is IPYNB, that stands for Interactive Python Notebook. JupyterLab, similar to the Jupyter Notebook, a browser-based application, but it is the new version of Jupyter Notebook. It allows you to access multiple Jupyter Notebook files as well as other code and files at the same time. So you can open a window and then you can access to different editors and different features at the same time. I will explain this a bit more. And Jupyter Hub, that is a multi-person version of Jupyter Notebook that runs on a server. Why do we recommend you to use Notebook? Well, because as I said before, it's a single document that combines text and explanation. You can have code and results at the same time. So this can be a complete documentation. and it helps you to share the outcomes of a project easily, and it gives you also the possibility to write and run code interactively, which is a very important feature. So in summary, if you use Jupyter Notebook or JupyterLab, you can produce you can provide reproducible research results, and you can make documentation of the whole process and project, which will be a complete documentation. And you can use it for making instructions, tutorial, and training materials. How does it look like? If you haven't seen it before, a notebook is basically composed of different cells, and of course a toolbar on the top. The toolbar is you can use it for the main tasks, copy, paste, cut, and running a code, stop, and so on. So you can explore it more. And the cells. So the cells, which are basically two types of cells, code cells and markdown cells. Here in this example, you see code cells, and before and after execution, you see by writing a code in each cell and run it, you can have also the output of this code as a result of this code in the same cell. As I mentioned before, this is a very important feature of Notebook, because you can have your code and results at the same time. Well, here you see some simple examples that is written in Python, but any other programming language can be used also. Another type of cell that is Markdown cell, that you can use it to add text to your notebook. For that, you need to know the Markdown's syntax for formatting this text. You can use these two websites to have some ideas how you can format your text. This is an example, simple example. You see, for example, the Markdown cells before and after running. And when you run this Markdown, you can have a clean document. Well, based on your taste, you can organize it, and then this can be also combined with code. You see, in this example, we have some text, and then we have a code, and then we have the result. And this is, in fact, the main feature that Notebook gives us. Here, I should mention that you can also add website link. Notebook can easily render this, and you can have the link in your document. And then after having this document, you can simply export it to PDF or HTML and share it with others. How you can make this notebook or generate this notebook? The traditional tool is Jupyter Notebook. We recommend you here the next generation, JupyterLab. As I said before, it gives other capabilities compared to the Jupyter Notebook. JupyterLab supports different or provides different editors, text editor, Markdown editor, CSV editor. You have also the file browser, you have terminal, so you can also open up other files in your browser in the same window, and by having different tabs. So basically, you will have a very organized, you can have a very organized project in one single page. And you should not be worried that if it is compatible with previously written notebooks with, for example, Jupyter Notebook, this is completely, JupyterLab is completely compatible with those existing ones. For installation, I recommend you to take a look at the documentation of JupyterLab. There is a very complete documentation to have some basic ideas how it works. You can first you can install Python from the website or Anaconda. And then using the pip or conda command, you can simply install JupyterLab over that. And when you install it, by running the command of JupyterLab in your command prompt or a terminal, you can open up a window in your browser, which will look like this figure. And you see in this figure, you have the main, the interface in your browser. So you can have access to your file. So there is a file explorer on the left side. So you can navigate through your directories and go to your file, the file that you aim, and even make a new folder and so on. And on the other side, you have also access to different programming languages. You can add here, for example, R language if you are R user, and other languages. It's not difficult to add other kernels to this to JupyterLab. That's by default is a Python. And then you can also add other applications and other functionalities that you need. This is an example. You see in this example, several tabs are opened in the same window. One is the a code, for example, that is a notebook with text, with the code and results, documentation. A figure is open here, so you can basically open and have different files at the same time. So if for example you double click on CSV file, you can open it with another tab in the main window, and then even you can, based on your preference, you can change these tabs and reorganize it as you feel more comfortable. This is another example. Here we used JupyterLab for raster data analysis. You see we have our notebook and code here, and then we have also the documentation, and even we open up a remote desktop, and we have also QGIS on the same area and analyzing the data from the same area, so we can have the whole project in the same in single window, and you can compare the results. As Mahdi said, we are lucky that EO Africa R&D Facility offers the Innovation Lab, which is a cloud-based platform, and it is based on Jupyter Hub and JupyterLab. So you don't basically need to install anything. You can go to the website, EO Africa website, register, and ask to access to the Innovation Lab. And by having that account, you can simply click on the Innovation Lab, and you can enjoy using JupyterLab in the cloud platform. For now, it is this platform supports some other programming languages and applications, and I believe that it is under development. So this will be soon with even other features, will be equipped with other features. So that's it from my side. If you have any question, please post it in chat. Then after the presentation, we can take a look and reply your question. In the following Serkan will show you some examples on the using JupyterLab and from different cloud platform. Okay, thank you very much. Serkan, floor is yours.
Okay, thank you very much. Thanks for this nice introduction to JupyterLab, and I thanks the other Mahdi for his nice introduction to cloud computing. While they were presenting, I was trying to answer the questions, but now I see that, in fact, I just replied to the panelists and the host, so the participants couldn't see the answers. So I kindly ask you to copy paste, please, what I say to the others. Meanwhile, I will share my screen, and in this part, in fact, I want to show you how JupyterLab works, as explained by Mahdi, and I will also demonstrate how to access Earth observation data on the cloud by using interactive notebooks, and how to visualize them and how to analyze them. So here we are on a cloud platform, and we are connected to the cloud platform through the JupyterLab interface. So as Mahdi mentioned, you can also install JupyterLab to your own laptop. So if you install to your own laptop, you will see also a partly similar interface. What might be different is the number of options that you have. So in this case, we have different kind of notebooks, and we have also some applications that are installed on top of JupyterLab. JupyterLab has two main parts. The first part, which is on the left-hand side of the screen, is the file browser. This is a typical file browser that you can find in other platforms or even on your laptop. Basically, we have different folders, and by double-clicking the folder name, you can go inside the folder. And each folder, in fact, stores several different files. And just by double-clicking a file, you can open it. Once you open it, it is displayed on the right-hand side, which is the actual workspace area. As Mahdi explained, the Jupyter Notebooks has the capability to combine documentation code and the outputs together in a nice way. In this document, we only see a documentation example. So here we have a documentation cell, and in fact, it's a rich text document. So in addition to standard paragraph, we also see a nice table here. Of course, it can also display other content, so like images. And the nice thing is it can be really easily rearranged. So you can lay out your working environment also as you wish. You can put side by side a code notebook on which you are working on, and next to it you can open a documentation where you can read the definition of the functions or how the functions should be utilized. In order to create an interactive notebook, you go back to the launcher, and then you choose the language that you want. So in this case, I open a Python notebook. That means I can write my code in Python. Very basically, I can create a string and then print it. So here, as you can see, the JupyterLab automatically highlights my code according to the syntax of the language. Here we have a very basic string definition, and then we are combining it with another string and printing the result. As you can see, the output is displayed just under the code cell. So you can also use another language. to write your code. So, for example, you can create a R notebook. And in that case, you can define the same string in R and print it by using the print command of R. And if you run the cell, you get the output as you get with Python. So basically, the interface and the language are quite easy to use. If you know Python or if you know R, you can start using JupyterLab immediately. It's really quite easy. Of course, you may need to upload some of your files to the platform. So in this case, you just click the upload button. And by clicking the upload button, the system will open a file browser from your local machine, where you can select the file to upload. And then the system automatically uploads the file to the Active Directory. And by double clicking, you can open it. And in fact, this is the example notebook that I will use for demonstration. So this is basically how JupyterLab works. So we will have some training courses about JupyterLab. So if you follow the activities of EO Africa R&D, you can get a detailed training on how to use JupyterLab. Our intention today is partly different. We just want to show you how you can access Earth observation data on the cloud by using JupyterLab or interactive notebook in general. For this demonstration, I will use Spatial Temporal Asset Catalog client of which is available in Python. So if you saw similar webinars or some tutorials which tells you how to access Earth observation data and process it, and so traditionally the way we process the data is to go to their websites. So as Mahdi mentioned, we have petabytes of data available, and luckily they are freely available. So you can download the data, but you have to download the data. So you go to a browser, you select your study area, you look for the data sets, you find the data sets, and then you start downloading the data sets. You keep them somewhere, and then either you process them locally or you upload them in another cloud platform and then start processing. Today, we will do something else. So instead of doing this downloading, uploading part, we will access the data directly. Stack, in fact, allows us to do that. Stack is a new development. Basically, it helps us and also the platform providers and the data providers to provide a common interface to access the data. And the goal is for all providers of temporal spatial data, which includes all this imagery, SAR, point clouds, to expose their data in a standard way. By using this standard, we can easily look at their catalogs, query the data, and download the data. In the demonstration, we will do exactly that. We will select a study area. We will select a time period that we are interested in. We will query for the data. We will download first a low resolution overview images to see what we have. And then we will focus a smaller area and retrieve the actual data, create a natural color composite, and then display it. For that purpose, we will use Sentinel-2, Level 2A auto-rectified atmospheric corrected surface reflectance dataset. As you know, Sentinel-2 is a ESA mission. So it is a wide swath, high-resolution multispectral satellite with 13 spectral bands. And as Mahdi mentioned in his presentation, with 2 satellites, it's possible to have a 5-day recurrence at the equator. So it provides a nice frequent data. This data is available at different data providers. Today, we will use AWS Open Data Portal. So here, the data is publicly available and for free. It is the exact copy of the original Sentinel-2 public dataset, and it covers data starting from April 2017. The data is available as cloud-optimized GeoTIFFs, so it's also very quick to retrieve, which is a nice thing for cloud computing purposes. Of course, you can use other data sources. For that purpose, you can check Stack Index, which lists all the data providers and all the different of data that you can find. How do we connect to the catalog? So for that purpose, we need to write a Python code. So first, we import the Python library to connect to the catalog. We define our study area. In this case, this is Bombetoco Bay in Madagascar. And for the time period, I choose August 1st to August 10 of last year. We are setting up our client, and we call the search function with the collection that we are interested in. This is Sentinel-2 Level 2A collection for our time and for our bounding box. And here I am running the code. So, and the result is that in the archive for Bombetoco Bay, we have 4 different images that are available. So what is the information that is available for these images? So just I am looking the properties of the first image, and I can see the retrieval date of the image. I can see the product ID and the cloud coverage, when it is created and in which UTM zone it is located. This information is nice, but it doesn't tell me where it is exactly located. So it's difficult to visualize unless you know by heart what these UTM zones and regions means. But we are in an interactive computing platform, so that means we can do some visualization in the same place. So here in the next cell, we are doing such a display. For that purpose, we are importing a geographic extension, a library. We are creating a geodata frame by using the data that we retrieved, which is in fact just the metadata. So we didn't retrieve the actual data yet. And we are creating the granules, the boundaries of these images, and then we are drawing the figure. And when I run the cell as an output, now we see the boundaries of these data sets in a nice figure. So the location is indicated. We know the latitude, longitude, but where on the map it is, we don't know. So we can do better. And the better way to do that is, in fact, to create an interactive map and put this information on top of this interactive map. And in the second cell, in fact, we are doing exactly this. So we are loading an interactive mapping library. And with this library, we are adding first our study area on the map. Then we are adding the granules on the map. And then we ask the map to zoom in to that area. And then just by using a single line of code, we can display the map. And this is the output of the map that we have. So here we have OpenStreetMap in an interactive manner. I can easily go the region that I want to. The granules that I asked to be added to the map are added with the tooltip information that is provided. So when I move my mouse cursor, I get the information regarding the granules. And I can see also with the red rectangle my study area. So now I know where I'm looking for and what kind of information is available. So what are the actual images? So let's try to retrieve them. So for that purpose, we need to load the data. How we load the data? We are importing the library that is necessary for that purpose. We are setting a stack configuration. The stack configuration basically tells us, the client in which bands we are interested in. It is also possible to name the bands according to our own preference. So in this case, normally the bands are numbered from 1 to 13, but we rename them as red, green, and blue bands. And then we ask the stack server to provide the data. And now I'm running the code. Here, as you can see, the system told me there are 4 different data sets. And because we are asking for an overview, the resolution is now quite small, but the data is there. It didn't take much time because the system is clever and it doesn't download the data unless it is necessary to download. And this necessity only occurs when we start to process it. So one type of processing is, of course, to combine different bands. So here in the next cell, we are importing the package to combine these different layers, and we are creating a natural color composite. A natural color composite of all these 4 different images that are available. So now the system is connecting to the data provider. It is extracting the data from these big granules, resamples it to a lower resolution, and provides me the data in only 16 seconds. Thinking that way, each data set is in fact about 800 megabytes in size. So in 16 seconds, in fact, we processed about 3 gigabytes of data. So it's really quite fast. We already saw that mapping capabilities are available. So now I will create a second map. In this map, I will still add my study area. I will add my granules, but in addition to that, I will add all the images to the map so that we can see. Here, I'm running my code. And as you can see now, we have an interactive map with the images displayed. So I can really see the images. I can see the granules. I can also even interactively turn off the granules or turn off any image that I want to. So I can only open one and I can focus. Because it's a low resolution image, we have these large grid cells. So we cannot see clearly the actual data. So let's try to retrieve the actual data to see it in a better resolution. So in the next cell, which is really very simple, we are just redefining our study area. We are focusing now a smaller area, and we are asking the system to provide us this data. It is already finished. As I mentioned, it is not loading the data unless it is necessary. And with this cell, we are creating a color composite, which is finished. So in 4 seconds, it downloaded the image data that we asked for. And let's display it. Instead of putting it on the map, this time I will only display the image. And this is the high resolution image that we have. This is the first image. As we have multiple images that are available, I am now selecting the second image by setting the second time. And if I run the cell again, then I receive the second image, which is different from the first. Of course, it is difficult to see what the difference is. So a better way could be, in fact, to put them side by side. So, and in this cell, I am exactly doing that. And now we see these 2 images side by side. This is the first image. This is the second image. And because the river is quite active, within a few days, in fact, these islands change the shape already. We took the data, we processed the data, we visualized the data. Of course, we may want to save it for other purposes, right? And this is also possible. So, and it's also relatively easy. We just need to load the library that is necessary to save the files as GeoTIFFs, which is a single library. And then one by one, the code will save the files to our cloud computing platform. So, and on the left-hand side, as you can see, the files are started to display. So we have 4 different overview images and 2 high-resolution images that are available. Now I can very easily right-click and download it to my own computer. I can save it, and I can also open it with a photo viewer or with QGIS, for example, for further processing. But cloud computing doesn't mean you need to use only interactive notebooks. In fact, if you want, you can also use desktop applications in a cloud way. For that purpose, now I am starting a remote desktop connection. Now I am in the same machine and I'm accessing the same files, but now I have a desktop with QGIS that's available. I run QGIS, and then I will without any data transfer, I will directly open the images that I just created. Very simply by selecting them. This is it. We have the images. As you can see, when I zoom in, this is the boundary where I have a high resolution image and where I have a low resolution image. And the good thing is these TIFF files are geolocated. So if I put a background map like OpenStreetMap, you will see that they have actual coordinates. Basically, this is the new way of working with geospatial data. So as you saw, I didn't switch to any other application. I didn't switch to any other platform or data provider. Just using my notebook, I queried what I want to. I received the information, I processed the information, I visualized the information, and make it available also for further processing purposes. If you want to learn more about this, as I mentioned, EO Africa Innovation Lab is such a platform which you can use. You can access the platform by following our activities, or if you're a researcher, you can also ask for research support through which you can access such a platform. With this, I will finish the presentation. And if you have any questions, I think we will be happy to answer.
Thanks, Serkan, for the great presentation. And also Matti for your presentation. Okay, let's answer some of the questions of the participants. But before that, I would like to paste a link of a web form. Please fill in the form if you have time. It will take just 1 minute. I paste it in the chat. Okay, let me read some of the questions, and then Serkan and Matti can answer your questions. I can also participate. Kennedy has a question saying, how are you sure the sensors are collecting good and reliable data, and how to calibrate with local conditions? What are security and data property issues raised with Earth observation cloud computing? Maybe Matti, you can answer the first one, and then Serkan can continue with the second one.
Well, regarding the Earth observation data, of course, there are several filters that you can apply before downloading the data. About reliability of the data, this is part of the game. Of course, you need to make sure about the resources. If the resources, the data resources are reliable, I suppose the Sentinel data are quite reliable resources. And yeah, I don't know if I understood it well, but there are, for example, if you think about I don't know, cloud coverage and these things, of course these filters are available, and also the processing level. You can apply these filters before accessing to data and before retrieving information.
Mm-hmm. Maybe I can also add that ground data is also something that is complementary to this. So of course, Earth observation data is nice because you can access it easily, but if it is combined with the ground truth data, it becomes much more valuable. So regarding the security aspects, so of course, that's something we need to consider. Eventually, if you move your data to the cloud, you rely on the platform provider to keep it safe and secure. from safety point of view, in fact, it can be better to use cloud infrastructure instead of your own laptops, because if something happens to your laptop, you may lose your data if you don't have your backups properly. Whereas in all modern cloud providers, this backup function is already provided. So your data is distributed to different places. And even if one copy has an issue, it is replaced with the other copies. So the continuity of your work is guaranteed from that point of view. For the security aspects, of course, that is always challenging. You know, the security is all getting better, but the attacks to security points are also, of course, increasing in time. What you can do, first of all, if you are working really with some sensitive private data, one option could be to have a local infrastructure in place. As we mentioned, JupyterLab can be installed locally, or you can create a local platform by using Jupyter Hub, which is a multi-user version of it. It is not very difficult to deploy, so that can be a solution for you. Otherwise, I think with the modern platform providers, we don't have a significant security issues.
Okay, thank you, Mahdi and Serkan, for your response. First, I share the link again. It would be accessible for everyone. I have another question from just looking at the chat. I want to ask this question, Serkan and Mahdi, please provide some information. What is the difference between different platforms, cloud computing platforms? Should we go, for example, for Google Earth Engine, or should we go for Innovation Lab or other platforms that are available there? What is your suggestion?
Okay, yeah, because we had limited time, unfortunately, we couldn't demonstrate how Google Earth Engine or other platforms function, but we can highly suggest, of course, all the interested people to have a look at those platforms. Eventually, they are there because they provide different kind of solutions. In case of Google Earth Engine, it is a complete system. So in my demonstration, it is nice to be able to do all of this, but in order to be able to do them, you need to know. You need to know all these packages and how the packages function. So you need a little bit programming experience, and you need to be able to integrate different packages that are available to come up with a solution. In case of Google Earth Engine, we have a single platform, and we have a single programming language, and all the libraries are provided by the same provider. From that point of view, it might be much more easy to learn, but what you learn will be limited to that platform. So you cannot move this knowledge to another platform. Whereas if you work with Jupyter Notebooks, you can save your notebook and upload it to another platform provider and continue to work from there. It's very convenient.
Well, accessibility would be also the main factor that you should consider when you're going to work on one cloud provider. So you should check how much resources do you have access, and if this fulfill your need, of course.
Okay, thank you very much. Let me just read the last question, and then we can close this meeting. Because we are 5 minutes over time. Ahindra Siva, if I read correctly, is asking, is it possible to find vegetation indices in cloud computing platforms?
Yes, in fact, well, first of all, you can very easily compute your own indices, because as I demonstrated, accessing the data is very easy. And doing computation on the data is also very easy. So just by doing a simple arithmetic computation, you can create the indices. But some of the platforms are in fact providing pre-calculated indices for certain time periods on their repository. So I believe Google Earth Engine has a 15-day composite NDVI globally. And probably you can also find it on other data providers.
Okay, thank you very much. Thank you very much for the answers. I would like to first share the link again. If you haven't had time to answer the questions, please do it. And let me just close the meeting by providing some information. Let me share my screen. So we had the question and answer session. I just want to say that this was the first webinar in the series of webinars from EO Africa R&D Facility. We will have another webinar on 20th of February, and then you can see the registry, some information about it on the EO Africa R&D website. Please go to the website and register for that webinar if it seems like an interesting event for you. And also there will be other webinars. You can see the list here. We will announce them in the next one after another in the next few months. I just want to say thank you for attending this seminar, and I wish you a pleasant day. Thank you very much. Goodbye.
Thank you. Bye-bye.
Bye.